In this video, I'm going to explain or at least explore the standard unit vectors, what they are, how we use them, and why they're convenient. Okay, so we're going to go ahead and start just by defining what they are. These standard unit vectors, you can already infer from their names, are 1 unit in length, but we say these are these vectors that you see I have graphed here, where we say I is this vector in component form 1, 0. Okay, so I is this vector that goes from the origin out to 1 unit to the right here, and j is given as always understood as being the vector that has the component form 0, 1. Okay, and so we refer to this as vector I, and this is vector j here, okay? And so vectors I and j, we often refer to these things because, keep in mind, often when we talk about vectors, we refer to them in component form, okay? And so that's exactly what these things are here, but what I want to do is a hypothetical. Let's say we had some vector v, and it proceeded out to this point, and we'll call this point v1, v2, okay? And so this would be our vector here. It would start at the origin, and it would head out to this point right here. When we talk about the x component and y component of this, we know that anything in component form starts at the origin. So basically, we value these components so heavily because what they're doing is they're telling us the x component and the y component, respectively. What I would like to argue is this. Anybody who's done vector addition before knows that when you add two vectors, say add this vector plus this vector, what we're really doing is we're taking it and sliding one of these vectors, say this one right here, over on top of this one here, so that its initial point lines up with this one's terminal point, and then we'd say the resulting sum is actually from the initial point out to the terminal point. We'd say this is the sum of two vectors. What I would like to argue is this, and perhaps I'll switch colors here. I would like to argue that every single vector that we're ever given can be rewritten as the sum of a bunch of i's and j's. And so another way to look at this is if I had a vector, hypothetically, we say this is the vector 3, 2. This would be the vector where I would have to go 3 out to my right and 2 up in the air to get to its terminal point from the origin, where it has an x component of 3 and a y component of 2. Essentially what I'd like to do is say that really we could say this is like an I vector, which goes from here out to 0, 1, plus another I vector if I arrange it head to tail, plus another I vector. What we could say is this is really just 3 i's right here. And another way to look at this is like saying, well, 3i, well, if I is just 1 unit in this direction, this is I, this is vector I, then we'd say, well, then 3i would be this vector that's 3 units in length. Now, if I add that together with a j and a j here, which is 2 northbound vectors here, then we really see that this becomes 3 i's plus 2 j's. And so I do want to make this a little bit clearer. So we say any vector v, any vector in the world, can be rewritten as the sum of standard unit vectors, okay? So instead of writing our vector here as 3, 2, we could rewrite it as 3 i's plus 2 j's. And so our goal is to be able to go from component form to this form, which you can probably see just by looking at it isn't that difficult, okay? So we say any vector v, which is v1, v2, we could rewrite this as v1 times this vector here plus v2 times this vector here. Remember, when you scalar multiply, you can just scalar distribute through these. So we'd say this would be the same thing if you wanted to consider this as v1 times 1 is v1, and then v1 times 0 is 0. And we say this is plus now v2, which is the y component of our vector. And we say v2 times 0, 1 would be the same thing as 0, comma v2. And remember, when you add two vectors together, you add their components. So v1 plus v2, v1 plus 0 is v1, and then comma 0 plus v2 is v2. Essentially, the original vector, v1, v2, which is this guy here, could be split apart and written like this. And if it can be split apart and written like this, we could factor out v1 and v2 here. Long story short, we know that 1, 0 by definition, we're going to call this the vector I. And we call the vector 0, 1, we'll call this the vector j. But essentially, we could say we have v1 of these i's and v2 of these j's. This is so true, so much so that if we said, let's take a vector 2, 5, let's write this as a combination of standard unit vectors, a linear combination of standard unit vectors. We could say this is 3 i's plus, not 3 i's, 2 i's plus 5 j's. And the reason it is the way it is because if I went right 2 up 5, and we say here's my vector, and this is the vector 2 comma 5 right here, that'd be the same thing as saying let's take 2 i's plus 1, 2, 3, 4, 5 j's, and our answer would be this resultant vector right here after we put these things so that their initial points line up with terminal points, and we go from the initial point to the terminal point. We get that this number here, instead of just being 2, 5, is actually also indeed 2 i's plus 5 j vectors, okay? So a couple things. First of all, v1 and v2 here, remember we call these the x and y component of our vector in component form. And also we can write v1, v2 as this, which is v1I plus v2j, and this is called a linear combination of the standard unit vectors I and j. So where we might see something like this, let's say, well, let's let the vector u, let's let this be the vector with initial point negative 2, 6. So it starts at negative 2 up 6. 1, 2, 3, 4, 5, 6. We say it starts here, and it ends at negative 8, 3. So negative 8, and then up 3, 1, 2, 3. So we have its initial and its terminal. If we draw this in here, we say this is some vector going in this direction. What we want to do is write this as a linear combination of standard unit vectors. So there's two ways to interpret this. My first one is to do this. Essentially, let's slide this so that it's down at the origin now. Let's put this in a component form. So I'd have to go, let's see, down 6, right 2 to get from here to here. Okay. If I also took this down 6, 1, 2, 3, 4, 5, 6, and right 2, we would say then my vector, if I had it in standard position, starting at 0, 0, would be this right here. And so essentially, the original vector in component form can be written this way. We say left 1, 2, 3, 4, 5, 6, so left 6, and down 3. This would be our initial vector in component form. And of course, we could have found this. By the way, the long way to do it is this. We say we'll take our x value of our terminal point minus the x value of the initial. So we say negative 8 minus a negative 2. And then this plus a positive, and so you get your negative 6 here. And then we say we'll take our positive 3 minus a 6 here. We say 3 minus 6, and then we get negative 3 here. Okay. So we say here's the component form of our vector. Our job is to write this as the sum of standard unit vectors I and j. So really what we're saying is here we have like a negative I, another 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 negative 6i. So we say negative 6i, and we say we'd go down 1, 2, 3. So negative 3 of these j things. Remember, j goes 1 unit upward. Well, negative 3 times j would cause it to go 3 units in a downward fashion. We'd say this would be the sum right there. So really, if we had to do this the quick way, we'd say negative 6, negative 3. If I wanted to write this as the sum of standard unit vectors, we'd just say it's negative 6, which is our x component, times I, plus negative 3 times j, which is our y component, times j. And this would be it right here. And likewise, if we said we had a vector 3i minus 2j, this would be the same thing as 3, negative 2. Okay, we could draw this very easily. We could say, go right 3, down 2, 3 i's plus 2 j's, and this is a negative 2j. You get this resultant vector right here, which is our vector 3, negative 2. Cheers.